Good morning and welcome back to Math 098 Elementary Algebra. So last class we were talking about more of exponent rules. We talked about the product rule, the quotient rule, the power rule, the zero exponent rule, and the negative exponent rule. Good morning, Patrick. So we left off on problem number 3. We finished analyzing number 2 together. We talked about the idea that order of operations still applies in this case. And oftentimes it's helpful to simplify what's inside the parentheses first. So meaning you may have to use the product rule or the quotient rule or negative exponent rule within the set of parentheses first, and then we apply the power rule. So we're going to look at number 3, and I'm actually going to take a slightly different approach. So typically we would say let's simplify everything inside the set of parentheses, but I want to show you something very interesting. And it's an alternative approach, but just because you've taken a different approach than I do doesn't mean that either of us are wrong. They're just different paths to the same destination. So let me show you exactly what I ended up with, or let me show you the process that I'm going to take, and hopefully it matches up with your answer. Good morning, everyone. Thank you for joining me. Let's take a look. Okay, so for problem number 3, we have 6a to the negative 4th, b to the 3rd, all raised to the negative 2nd power. Now, typically, I may say, okay, well, we have a negative exponent here, so we'll circle it, we'll move it down, etc., etc. Good morning, Johanna. But instead, what I'm actually going to do is I'm going to know I have 1, 2, 3 bases. The power of my 6 here is a 1. The power of my a is a negative 4. The power of my b is a 3. I'm going to take this negative 2, and I'm going to apply the power rule. So I'm going to make a note of that. I'm going to apply the power rule, which means power times power. That's going to give me 6 to the negative 2nd power. A to the negative 4 times the negative 2 is a positive 8. And then b to the 3 times the negative 2 is a negative 6. At this point, I'm going to say, okay, I'm going to circle every base with a negative power. And because they're in the numerator, I'm going to shift them to the denominator. So that leaves me with a to the 8th over this 6 to the negative 2 comes down as 6 to the positive 2. B to the negative 6 moves down as b to the positive 6. And then we know that 6 squared is actually 36 because 6 times 6. So your final answer should be a to the 8th over 36 b to the 6th power. Doc, excellent work. And thank you, Noelia and Kayla, for sharing your answers as well. And Ryan, you as well. Okay? Notice the location of all of my pieces. We just have to be very careful in the way in which we do this. Okay? This was one approach. You could have taken that a to the negative 4th and moved that to the denominator first. So it would be 6b to the 3rd over a to the 4th. But that entire thing is being raised to the negative 2 power. So even if you distribute that negative 2 power, think about what's going to happen. Everything's going to switch locations, right? They're going to switch places because then they'll all have negative powers. So, I mean, the approach depends on you, but what you have to keep in mind is the rules, what the rules are and how you apply them. So yeah, Doc, excellent, excellent work. Now, we're about to look at a couple problems where we're trying to identify the missing exponent. And the only real way we're going to be able to do this is if we have a solid understanding of what those rules are. So, product rule, keep the base, add the powers. Quotient rule, keep the base, subtract the powers, leave it where it's heaviest. Power rule, you're going to distribute the power, power times power, right? Negative exponent rule, you take the base of the negative power and you move that to either the numerator or denominator, wherever it's not located initially, right? And then you change the power from negative to positive. And then the zero exponent rule, when a base is raised to the 0 power, it's equal to 1. So let's take a look at these two problems and see what's going on and figure out what that missing exponent is. So for number 1, we have 2g to the question mark. This is our missing exponent. H to the negative 4th, all raised to the negative 3rd power. Now, interestingly enough, I have the result of what I want it to look like. So notice here that we have 1, 2, 3 bases, and we also have 1, 2, 3 bases. So we know that we're not missing anything in particular. What we want to do is figure out what number, what value goes here in place of the question mark so that the left side ends up equaling the right. So what I'm going to do is I'm actually going to rewrite this. So we have 2 to the first, g to the question mark, h to the negative fourth, all raised to the negative third power. When we see that we have this power on the outside, immediately I can say to myself, well, let's use the power rule and see what happens. So if I use this power rule, I'm going to take my exponent or my power outside the set of parentheses, and I'm going to distribute power times power. So that gives me 2 to the negative 3, g to the, and then you have question mark times the negative 3. Can't I just say negative 3 question mark? So it means that there's a product here, negative 3 times some number. And then we have h to the positive 12. Okay, next notice that this 2 to the negative 3, this is going to move to the denominator. Okay, we also note that if this question mark is positive, this g will also move to the denominator, right? So we're starting to figure out, oh, I have to throw in a positive number in that question mark because I know that g needs to be in the denominator. So there's a hint here. I'm going to make a note that question mark must be a positive number. We just have to figure out what that number is going to be. So right off the bat, I see that h to the 12th remains in my numerator. I see that 2 to the negative 3 becomes 2 to the positive 3 in the denominator. And I have to make this so that my power becomes a positive 6. Now keep in mind, that negative implies that when I circle it and I move it, it's going to come to the denominator. So when you think about this, all you have to do is say, well, I need my power to be a 6, and I have a negative 3 times what gives me that negative 6, which implies that the question mark must be 2. If our question mark is 2, this becomes g to the negative 3 times 2, or g to the negative 6 power. When we have g to the negative 6 power, that moves down to the denominator as g to the positive 6 power. And that answers the problem. We figured out that the question mark is 2. If it's helpful, you can right off the bat replace the value with numbers that may work or may not work, but that's totally up to you. You can play around with this idea and determine what's going to work for you. Okay? So again, this is just going to take a little bit of practice. I hope that you saw that I distributed using the power rule, and I noticed that my 2 to the negative 3 moves down to the denominator, which 2 times 2 times 2 is 8. So they are the same, right? And if you would like, if it helps, I can write h to the 12th over 8g to the 6th check mark. So we prove that it is exactly the same. And the other piece is I had to somehow make this into a 6, a positive 6, but we know that because this base was in the numerator, the negative helps to move this base to the denominator. All right, let's take a look. Let's take a look at number 2. We have 4p to the 5th, t to the negative 2nd power, all over 12, p to the 1st power, t to the question mark, and the entire thing raised to the 2nd power. Okay, the very first thing I'm going to do personally is I'm going to simplify what I can in here. I do know what I want to get as a result. I know my final answer, my final simplified form should be p to the 8th over 9t squared. Okay, not a problem. First off, 4 over 12, again, if you want, write it as a fraction just so you can see this. Immediately you're going to tell yourselves, oh, I can reduce that. That becomes 1 over 3, right? Okay, so right now, when I reduce that, I have 1, I have a 3 here. Notice I have 5 p's in the numerator, but only 1 p in the denominator. So when I simplify, I notice that I'm going to have 4 p's in the numerator. But then I'm left with t to the negative 2 over t squared. So actually, what I may do at this point is I may say that this base with that negative power, so t to the negative 2, moves down. So now I have t to the positive 2 and t to the question mark. Okay? This whole thing is being squared. Hopefully that simplification wasn't too big of a deal, and you can see exactly how I took those baby steps just to see exactly what's happening. Okay, the next thing I'm going to do is I'm actually going to square every piece inside of here, which means power times power. So I've got power times power, power times power, again, again, again. That leaves me with 1 squared, p to the 4 times 2, which is 8, 3 to the 1 times 2, which is 2, t to the 2 times 2, which is 4, and then t to the question mark times 2, which is 2 question mark. Okay, this is what we have so far. Now notice 1 squared is 1, so that's check. P to the 8th, check. 3 squared is 9, check. But then somehow I want only t to the 2nd power down here. Recall that with your exponent rules, when they're right next to each other like this, t to the 4th times t to the whatever power, this is the product rule. So notice already we use the quotient, we use the negative exponent, and we use the power. What we're about to use is the product rule. So somehow I've got to figure out what number this question mark has to be in order so that when I combine these two, I'm left with a positive 2. I want a t to the 2nd power. Well, let's play around with some ideas. If I had t to the 4th times t to the 2nd power, well, that's t to the 4 plus 2, which is 6. But what if that power were negative? What if I had t to the 4th times t to the negative 2? Well, now I have keep the base, add the powers, and I'm left with exactly what I'm looking for. So notice here, my power is 2 times a question mark. Well, we need to make this power negative, so that question mark must be equal to -1. And that concludes our answer. Noelia, this is definitely a little bit confusing. What you may want to do is just kind of play around with this idea. And the major feeling behind this is try to figure out what values should go in place of the question mark so that the left side of the equation equals the right side of the equation. Okay? To kind of take this a step further, I'm just going to rewrite this bottom part. If I wrote 1 to the 2nd power p to the 8th over 3 squared t to the 4th and then t to the, let's make that a -2, check out what happens. 1 squared is 1, p to the 8th stays, 3 squared is 9, and then t to the 4th times t to the -2 is t to the 2nd power because you keep the base, add the powers. And check, we have exactly what we wanted. So we can make sure that they're completely identical. Okay, continue playing around with this idea. What I'll do is I'll actually give you an activity that you guys can try at home. So you can play around with figuring out what this missing exponent is. As you become really strong in all of your rules, that's going to help immensely too. So think about the behavior of these bases with their respective powers, okay? So I'll send out an activity that way you all can play around with this and then get really strong in terms of identifying that missing exponent, all right? Perfect. Let's continue looking at our notes. So now that we have completely covered our exponent rules, we are ready to move into other operations on polynomials. We talked about adding and subtracting already, and that was straightforward, right? You distribute to drop parentheses, you combine like terms, and that's it. You finished. When we talk about multiplication and division of polynomials, now we actually have an opportunity to apply some of the exponent rules, right? Like the product rule or the quotient rule. So we're going to take a look at those specifically as we move through this section. We might even finish Unit 6 notes today. Let's take a look. So we're going to start off by multiplying a monomial by a monomial. Consider a monomial as one term, so one-term polynomial multiplied by a one-term polynomial, 1 times 1, should be a one-term polynomial. That's a great way to think about how you multiply polynomials and what your result should be. So this is a monomial, right? There is no plus or minus separating terms. So this is a monomial times another monomial. We've actually already multiplied monomials, we just didn't call it that. Now we're ready to do so. So if we multiply, we're going to start with our numeric bases. We have a -3 times a 7, which is a -21. We then look at our common bases. We have x to the 5th and x to the 11th. Product rule, x to the 5th times x to the 11th means you keep the base, add the powers. We have y to the 4th times y to the 2nd, keep the base, add the powers. And voila, we're done. That's all we have to do. I'm betting anything that the multiplication and division of polynomials is going to be so much better than identifying the missing exponent. Let's take a look at multiplying a monomial times a binomial. Monomial, one term, so here's an example. Binomial, two terms. Here's an example of a binomial, right? Separated by addition or subtraction. Perfect. When you have a one term times two terms, you better have two terms, right? 1 times 2 is 2. All right. So what we're going to do, just like we did before, and if it's helpful, let's recall something you're used to. If I gave to you something like, let's do 7 times 3x minus 4y, you would say, oh, no big deal. I distribute 7 times 3x because it's 7 times 3 with an x, right? So it becomes 21x. And then 7 times a -4y is just a -28y, right? We are used to that. We've seen this before a million times. This time we just have more variables and we have different powers. Who cares? So let's do it. We have a -5m to the 2nd power times 11m to the 3rd. Okay, let's start with our numerical bases. -5 times 11 is a -55. And then 5 to the 2nd times, wow, m to the 2nd times m to the 3rd is keep the base, add the powers, m to the 5th. Now we're going to distribute the -5m squared to the -8m squared. Let's start with the numerical bases. -5 times a -8 is a +40. And then m to the 2nd power times m to the 2nd power is keep the base, add the powers, m to the 4th. And that's all you have to do. Let's do it again. For number 3, we have -4xy to the 2nd power times x3rd y plus 2x to the 5th. All right, let's write in some powers here. X is to the 1st power, y is to the 1st power. Let's distribute. Notice it's a monomial times a binomial. There are two terms here. So let's distribute. We have -4x to the 1st, y to the 2nd, times 1x to the 3rd, y to the 1st. You're probably thinking, where in the heck did I get the 1? Well, you know the coefficient of every term is 1 unless it's actually written in there. So I'm going to start with the numerical pieces first. We have -4 times 1, which is a -4. Next, we have x to the 1st times x to the 3rd, which is x to the 4th. And then we have y to the 2nd times y to the 1st, which is y to the 3rd. Keep the base, add the powers. That takes care of my first term. Now I'm going to take the -4x to the 1st, y to the 2nd power, and distribute to the 2x to the 5th. So let's start with the numerical pieces. -4 times a +2 is a -8. I have x to the 1st times x to the 5th, which is x to the 6th. And then we have y squared. And we're done. You wouldn't just erase the y squared. That's part of your term. So when you multiply, you simply combine your bases using the product rule. Keep the base, add the powers. Why don't you give number 4 a shot? mn to the second power times 6m to the fifth n to the fifth plus mn. Let's do 2 minutes starting now. When you have your answer, go ahead and type it into the chat. Excellent. Let's take a look. So first off, notice that this m is being raised to the first power. So it's m to the first, n to the second times 6m to the fifth, n to the fifth plus m to the first, n to the first. Oftentimes, it's going to be helpful. You might as well write it in there. So we're going to distribute. When you successfully distribute, you'll notice that 1 times 6 is 6. M to the first times m to the fifth is keep the base, add the powers. N to the second times n to the fifth, keep the base, add the powers. Next, we're going to distribute our second term. So m to the first n squared times m to the first n to the first. Notice it's still a positive 1, but 1 times our bases here, we'll just leave the 1 out. So we have m to the first times m to the first is m squared, and then n squared times n is n to the third. So excellent work, everyone. Noelia, Ria, Kayla, Patrick, Doc, excellent work on distributing here. Let's take a look at what happens when we multiply a binomial times another binomial. As a reminder, a binomial is 2 terms. So when you have 2 terms times 2 terms, you should have 4 terms. What that doesn't mean is that you won't have to simplify, right? That is still a possibility. So for instance, when we distribute and we get all 4 terms, it is possible that we will have like terms and we need to combine those. So we need to be careful to make sure that we simplify all the way, just not part of the way. We need to simplify all the way, which includes combining like terms. Let's take a look at this binomial, and I'm hopeful that you see how simple it is to multiply binomial times binomial or larger. Let's take a look. Typically speaking, if I had just a 3y in front of that set of parentheses, you distribute the 3y to each of the terms, correct? Now, what if I had just the 2x? If I had just the 2x in front of that set of parentheses, you would also distribute the 2x to each of those 2 terms. Well, that idea doesn't change just because we have a binomial in front of that set of parentheses. So what we're going to do is we're going to start with our first term, and we're going to distribute to each of the terms in the second set of parentheses. Duh, right? This 2x is in the first set of parentheses, so we want to distribute to what's going on in the second. Once we finish with the 2x, we then move to the next term in the first set of parentheses, and we say, okay, well, now I have to distribute that 3y. Think of it as each term in the first set of parentheses gets distributed to everything in the second, right? Every term gets their opportunity. So let's multiply. We have 2x times x. Remember, these are both to the first power. So 2x times x, we'll start by multiplying the numerical bases. 2 times 1 is 2. X times x is x squared. Keep the base, add the powers. Then we multiply 2x times a negative 11y. Remember, I didn't finish here until I distribute to everything in the second set of parentheses. So 2x times a negative 11y, that's going to give us a negative 22xy. Notice here, this term does not have an x, this term does not have a y, no big deal. You're simply going to combine those, and we get xy. I am now ready to move to my next term in the first set of parentheses. So 3y times x. Keep in mind, we'd like to keep our terms in descending order. This also means in terms of degree and alphabetical order. So if we have 3y times x, we're going to write positive 3xy. Let's put the x before the y. And then lastly, we have 3y times a negative 11y. Again, if it helps, write in those powers. So 3 times a negative 11 is a negative 33. And then y to the first times y to the first is y to the second. Keep the base, add the powers. Notice that we have 4 terms. Success. But also notice that I have like terms. My negative 22xy and my positive 3xy, these are both like terms. So we combine like terms by adding or subtracting the coefficients, right? We keep the variables exactly as they are. So basically, we're saying how many xy's do we have? Well, here I have negative 22 of them. Here I have positive 3. So together, I have negative 19 xy's. And we're going to bring down the last term and the first term to complete our answer. So our final answer is 2x squared minus 19xy minus 33y squared. Not bad, right? It's just distributing. It almost looks kind of like some sort of rainbows going on here. All we have to do is distribute. Go ahead and try number 6. Type into the chat when you're all set. All right, excellent work, everyone. Let's take a look at the process behind distributing this binomial times binomial. So we have that we are going to distribute the 5b first. So we have 5b to the first power times 4b to the first power. That's going to give me exactly, Doc. You're taking this nice and slow. You're essentially doing this very piecemeal, which helps a lot. And I urge you all to do exactly that. And thank you, Kayla, for that breakdown. So 5b times 4b is going to be 20b to the second power, right? B to the first times b to the first, b to the second. We then distribute 5b to the first times 3c to the first. So that's going to give us 15bc. They're both to the first power, so we essentially just combine those two. Next, I'm going to move to my 3c term, and I'll distribute that to both of the terms in the second set of parentheses. So 3c times 4b is 12bc. And then we have 3c to the first power times 3c to the first power, which is going to give us 9c to the second power. Excellent. At this point, you say, all right, let's combine my like terms. So my final answer should be 20b to the second power plus these two are like, so we're going to combine them, 27bc plus 9c squared. So excellent, excellent work. Patrick, I do want to point out that you had written 20b squared plus 9c squared plus 27bc. That is totally fine. I will tell you that oftentimes you'll see that when you have all degree 2, this is degree 2, this is degree 2, remember, because it's the total degree of a term, so 1, 1, the total power. So degree 2, degree 2, degree 2, they're all tied. So essentially then you look at alphabetical order. This one has B, so that definitely comes first. This one has BC, so this one comes next, and this one just has C, so that comes last. If you want to get in the habit of writing in this form, that'll be helpful, but you'll never get points taken off just because you place the 9C in front of the 27BC. Just something to think about. Okay, let's look at number 7 this time. Notice what's happening in number 7. This says 4m minus 7 to the second power, okay? Because this says 4m minus 7 to the second power, I want you to think back. Let's recall something that we've talked about before. If I had negative 5 to the second power, we would say this is the same as a negative 5 times a negative 5, which gives us a positive 25, correct? The idea behind this is that when we had that expression being raised to the second power, we wrote it out twice, and then we did the math. With these kinds of problems, we have to write it out twice. So we must rewrite this first. Okay, this will always be the case, hence all of the exclamation points. We must rewrite this first. Don't forget that. This might be another example that you'll put on an index card as a reminder, oh yeah, I've got to rewrite it first. When I say rewrite, I mean 4m minus 7 to the second power is 4m minus 7 times 4m minus 7. You have to write it out first. Then we can distribute. It is not enough to say, oh, let's just square each term. That power rule only applies to monomials. You cannot take a binomial, raise it to the second power, and just square each term and say, oh, this is just 16m squared and this is just a positive 49. No, 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 no. I'm going to prove to you why that doesn't work. So I've rewritten it twice, right, because it's to the second power. If it were to the third power, we'd have yet another one. So I'm going to distribute, just like we learned. 4m times 4m, that's 16m to the second power, right? If it helps, again, write out those powers of 1. 4m times negative 7 is negative 28m. Negative 7 times 4m is negative 28m. And then negative 7 times negative 7 is positive 49. Notice how many terms I have. I have 4 terms, because I was squaring a binomial, which means binomial times binomial, hence 4 terms. These 2 terms are like, so I'm going to combine them. My final answer is 16m squared minus 56m plus 49. If you had just squared each of these terms, you'd be missing that middle term. You'd be missing the negative 56m, which means your answer is completely incorrect. Okay? So be super careful. Put this on an index card so that you don't forget. So when you're studying, that's part of your studying cards. Okay? Go ahead and do number 8. We have 9p plus 4 times 9p minus 4. Type in the chat when you're all done. I love seeing all the responses in the chat. It's just fantastic. Thank you, Noelia. So we're going to distribute just like before. Let's put in some ones here for my exponents. So 9p to the first times 9p to the first is 81p to the second power. Then I have 9p times negative 4, which is negative 36p. Then I have positive 4 times 9p, which is positive 36p. And then I have positive 4 times negative 4, which is negative 16. Thank you, Kayla, for showing the breakdown. Notice that these 2 terms are opposites. When you combine opposites, you're left with 0. So a negative 36p plus 36p actually cancel each other out. And your final answer is 81p squared minus 16. Excellent, excellent, excellent. Now, what I'd like you to do is prove that you understand the process behind this idea of multiplying polynomials. Notice what we have in number 1. I have a binomial being multiplied by a trinomial. How many terms in a binomial? How many terms in a trinomial? So when you multiply those, how many terms should you have? Binomial, trinomial, 6-term polynomial. That's what you should be looking for. If you can combine like terms, you definitely should do that. I want to see how well you understand this concept. Try number 1. Give that a shot. We have 2n plus 3 times n squared minus 4n plus 1. And if it helps, I'm actually going to move this in a little closer. All right? I'm just going to give you a few minutes. When you have the answer, go ahead and type it into the chat. All right, let's distribute and see if you are all correct. So we start by distributing the 2n to each of the terms. 2n times n squared. If it helps, again, write a 1. That becomes 2n to the third power. 2n times negative 4n becomes negative 8n to the second power. 2n times 1 is a positive 2n. Thank you, Gia. That's awesome. Next, we move to the 3. So we're going to distribute the 3 to each of the terms. 3 times n squared is 3n squared. 3 times negative 4n is negative 12n. And then 3 times 1 is 3. Awesome. Notice 1, 2, 3, 4, 5, 6 terms, which is exactly what we expected. Now all I have to do is combine like terms. So first off, I notice that I have my largest term, which is 2n to the third, and there is no other like term. So I'm simply going to bring that down. Next, I have negative 8n squared plus 3n squared. Well, that's going to give me negative 5n squared. Next, I have 2n minus 12n, which will give me negative 10n. And then lastly, I have a positive 3. Excellent work, everyone. That was absolutely fantastic. I love all of the work that you put in here. Be very careful with all of those signs and be very deliberate in terms of, moving through the process. Like Doc had mentioned, slow and steady wins the race, basically, right? Make sure you're taking this step by step. Okay, last challenge problem of the day. I have 8, 9, wow, yep, let's try talking correctly. I have 8n plus 3 to the second power minus, parentheses, 7n squared minus 11n minus 1. Let's see what you got. I'm actually going to leave you with that problem. Tomorrow's class, we will come back to this one, maybe take a look at a couple other examples to make sure that you're totally set. And then we'll move into the very last section of these notes, which is division of polynomials. Thank you so much, Claire. I will reveal the answer tomorrow during class. All right? Continue to work on this problem right now. You still have a couple minutes left of class. Really break this down piecemeal. Think about the process behind this. And yeah, let's see what you have for this problem in tomorrow's class. All right, everyone, enjoy this gorgeous day, right? We finally are back in warmer weathers. It's insane. Enjoy. I'll see you all tomorrow. Bye.